Welcome back, folks. We're going to do another mesh analysis problem. We're looking for the mesh currents, and we're going to use those mesh currents to find the other values in the circuit. Now, it's a little bit of a different circuit. We have a second voltage supply. Okay, here, let's just have at it. There we go. We have a second voltage supply. Okay, now previous methods, you might not have been able to analyze this circuit if you have more than one supply. You might have had to simplify it. Well, maybe you can hope that they're going to end up in series, but in this case, they're not going to end up in series. Furthermore, if you had some circuit analysis in your physics classes, they might have encouraged you to crunch down all the resistors into one, figure out the current, and then work your way back up. That's fine, and they probably use the concept of R total, and I absolutely hate the concept of R total because, well, which supply are you going to lose? Okay, you can't do that with two supplies. Which one are you looking from at any given time? So it's limited. Those analysis methods are limited. With mesh analysis, piece of cake. Okay, you just treat it as another voltage, you include it in your KVL, and you're good to go. So it's another problem. We're just getting our feet wet with mesh analysis. I think it's not a huge leap in what we did from the last video, but I want you to realize that with mesh analysis, you can start to analyze more complicated circuits. Maybe they have multiple supplies. This one has two voltage supplies. So let's go ahead and do it. The mesh currents are already labeled. I just had the figure already drawn that way, so we're going to go with it. And this one is clockwise, and this one is counterclockwise. I've said it a few times. It doesn't matter what direction you pick. You can mix and match. When you get to the shortcut, you're going to want to do them all in the same direction, but we're not there yet. And that's kind of why my habit has turned into do them clockwise. But there's no reason you have to do them all in one direction. There's no reason you have to do them all clockwise. You could do them all counterclockwise. It all works out as long as you follow the steps and pay attention to your polarities. So let's go ahead and do this. And it looks like we've got this bluish color over here. I'm going to write a KVL. You can see that the polarities are already labeled inside the mesh according to the passive sign convention. So I'm going to write a KVL up here, and I'm going to say I go up 12 volts. That is a wrong color. Ready? I go up 12 volts. I go up VS. Let's stay symbolic for now. I go down VR1. I go down VR2, and at 0. Okay, VS is going to be 12 volts. VR1 is I1 R1. Okay. I2 doesn't touch it. I1 goes in the positive direction, and we multiply by R1 to make it a voltage. VR2 for this blue mesh, I1 mesh, right, is over here. And we say, let's see, I1 flows in the positive direction, I2 flows in the negative direction, and we multiply by R2. Do some substitution in order to make this all work. VS minus I1 R1 minus I1 minus I2 R2, and that's equal to 0. Okay, getting closer there. That's our KVL for the I1 mesh. So maybe I should label that up here, KVL for I1. Okay, let's see. Doing the same thing for I2. I'm going to start here. Now pay attention to your polarity. Oh, maybe I should go around this way. Maybe I should go around this way. Okay, so I'm going to start here, and I'm going to go counterclockwise. So I'm going to go up across the 8 volt. So this is VS2. Ooh, this is VS1. 1, 1, and 1. Since we have two of them now. Okay, VS2. And then I'm going to go down across R3, and I'm going to go down across R2. And I'm back to where I started, so that's equal to 0. So here's VR3 and VR2. And I'm following these polarities, these yellow polarities. All right, VS2 is 8 volts. Oh, I remember this problem. This one's fun. There's an Easter egg. VR3, we'll get there. VR3 is I2 times R3. And VR2. Oh, I made a mistake over here. I wasn't paying attention to polarities. This is why habits are so important. This is why habits are so important. I did it as if... Okay, I'm going to fix that in a second. VR2. Positive direction. This is what I screwed up. Okay, positive direction according to that polarity is down. I2 and I1. Did those out of order? Doesn't matter. Are both positive. And that's R2. And that's what I screwed up over here. Because the positive direction according to this bluish, light blue, polarity is the same, right? It's also going down, and they're both going to be positive. I almost made a sign error. Turns out I'm not perfect. Neither are you, but we got to try to be. Okay, we've got to build good habits. I did something out of my habit, and I almost paid for it. Okay. I'd rather show you that than erase it. Again, I could edit these videos and make everything look pristine, but life is a little messier than that. Okay, so the minus sign comes down. We plug in I2R3. The minus sign comes down, and we've got I'm going to make this I1, I2, switch those around. Okay, it's mathematically no different. Oh, and it's behind me. There we go. Okay, I'm feeling better about that. Feeling better about that. A little bit of algebra. Okay, so we're going to distribute and regroup. VS1 minus R1I1. I'm going to flip around so the resistors are, the coefficients R2I1. So I get the minus distributed in there and the R2 distributed. And then the minus is going to distribute over here, and the R2 is going to distribute. And we get I2, and that's equal to 0. Grouping like terms, here's my I1 terms. All right, so it's going to be negative R1, negative R2, I1. And, oh, this is just playing with my head because they're different directions. Negative R2, I2. Okay. Bringing VS1 over, it's going to be negative VS1. Okay, and that's in a pretty good form. Really all that's left for me to do is plug in some values. Let's go ahead and do that. Negative 6, again, I'm looking at my notes, but by all means pull up the image of that I'm writing on right now. I'll post it with the video if you need to look at the schematic at the same time. Okay, so negative 6 and negative 12, I get negative 18, I1. And negative 12 I2, and that's all equal to negative 12 volts. Okay, and there's my first equation for my system of equations. Okay, we got some artifacts up here from the green screen. Sorry about that. Doing the same thing for the KVL for I2. VS minus R3 I2 minus R2 I1 minus R2 I2, and that's equal to 0. This is VS2, isn't it? Okay. Let's see. That's our only I1 term, so we get negative R2 I1. And then here's my habit again. I'm not going to break it this time. I'm going to put plus and a parentheses because I know I have two terms that are I2 terms. So negative R2, negative R3, and that's in front of I2. Bringing VS2 over, so it's going to be minus VS2. Okay. Plugging in values. Negative R2 is negative 12, I1. And then we've got negative 12 and negative 12, so that's negative 24, I2. Over here we got negative 8. And there's the second equation for our system of equations. Oh, it's behind me again. There we go. Still getting used to that. Okay, so Let's see here. We got to get this in matrix form, so let's do that in white. It's going to be a 2 by 2 matrix because we've got two unknowns. Okay, I'm going to invert that. And multiply it by the right-hand side, and that's going to give me my vector of unknowns. I1, I2. Okay, the order here determines the order of the coefficients here. Hopefully you've seen that in my other videos, but keep in mind that that order is important over here. Okay, so we're going to get these two equations in. I'm going to take this first equation, and let's take the coefficient of I1 as -18. The coefficient of I2 is -12, and the right-hand side is -12. Okay. Taking this one, the coefficient of I1 is -12, the coefficient of I2 is -24, and the right-hand side is -8. Okay, you're going to solve that any way you want. I encourage you to either pause the video or do it along with me while I grab my my old faithful calculator here and we figure out what's going on. I probably have the answer somewhere. I do like working it out by hand every time. It's good practice. It's like exercise for your brain and, in this case, my thumbs. So I make sure that my calculator skills don't get rusty. Okay, so let's see what we got. Okay, so we got 666.7, looks like 2/3 of a milliamp. Okay, or 2/3 of an amp, 666.7 milliamps. Okay, and then here's your Easter egg. It's a fun one. Ready? 0 amps. Okay, everybody loves when you get 0 as an answer. It always makes you go, did I screw up? You didn't screw up in this case. Okay, it actually does end up being 0. Okay, so this current ends up being 0, which is very interesting. And this is 2/3 of an amp. So let's use it. Ultimately, what we're trying to do here, I didn't write this, is again find VA, this VA here. So let me get a different copy of the schematic. Come here. There we go. And let's go ahead and find VA. Now, the polarities are a little less confusing in this because it's plus on top and minus on the bottom. So that kind of lines up with VA with respect to ground. So we can use either of those polarities. It fits on the blue side, so we're going to go with that. And in order to find that voltage, we can kind of use the same formula here, but we got to be careful with polarities, right? I1 goes in the positive direction, since that's the positive direction of current. I2 also goes in the positive direction. It's 0. We would have gotten away with it. And then we multiply by R2. Okay, so that's going to be 2/3, or 666.7 milliamps, plus 0 amps times 12. So 2/3 of 12 is 8. All right. So this point, well, if we look at this voltage supply, this point, this node, is 8 volts with respect to ground. This node is 8 volts with respect to ground. This one over here is 12. Okay, 12 volts with respect to ground. This current being 0 is only possible because the voltage on either side, the potential energy on either side, is 8. So there's no difference in energy on either side of that resistor, and there's going to be no flow. I think of this as a kind of like a siphon. Oh gosh, I'm going to draw for you. Okay, if we get two containers, I'll give you a little more perspective. Curve the bottom there. Right, if we get two containers and we have them at different heights, we can create a siphon. And let's throw some water in here, right? I told you I was going to draw. I'm regretting it already. Okay, and we take a tube of some sort. Let's just make it a white tube, right? And we put the tube from here into here. Now, if I hold the two cups level, there's no difference in potential energy, and there's going to be no flow through that tube. In order to get any flow, I have to create a difference in potential energy. And that's what's happening here. There's no difference in potential energy, so there's going to be no flow of current through that resistor. Okay, so I moved a little quicker, half as long as the last video. I moved a little quicker. We can start to move even quicker as we get more comfortable with this. And we worked a problem that we might not have been able to do before, because we can now work on problems that have multiple voltage supplies. Okay, so we're going to work another problem. I think we're moving to even more meshes. I said this scales, and we can work on more complex problems, and it does without a problem. So that's what we're going to do next. So stay tuned and good luck.